Good day everyone, we are Group 6 composed of A. Patrick Avellanosa, Kasi Angeli Figuracion, Jan Isaac Aquiliano, and I am Jerome Pulmeño. Today we'll be presenting our project titled Introduction to Machine Learning, House Prices Advanced Regression Techniques. So in this presentation, we'll be discuss how machine learning can be used to predict house prices using various data features and regression models. Our aim is to show how data and algorithms can help make accurate predictions in the real estate market. To begin our discussion, machine learning is now widely used to solve real-world problems, including predicting house prices, by analyzing features like size, location, and quality. ML models can help buyers and investors make better decisions. In our study, we use a housing dataset containing details about various property features and apply proper data processing to clean and organize the data. So this step helps improve the model's accuracy. Lastly, we tested different regression models to determine which one predicts housing prices most effectively. After collecting and organizing the data, here we can see the descriptive statistics of the sale price variable in our dataset. It includes 1,460 houses with an average sale price of around $180,921.20. So the price range from $34,900 to $755,000, showing a wide variation in housing values. The median or 50th percentile is $183,000, which means that half of the houses are priced below this amount and half above. So this gives us an overview of how the housing prices are distributed before applying our machine learning model. Lastly, this figure presents the relationship between sale price and overall quality. It shows that as the overall quality rating increases, the sale price also tends to rise. This indicates that the housing quality is a major factor influencing property values. And that concludes the descriptive statistic part. And next, Isaac will continue the discussion.
Hello, I'm Jan Isaac Aquiliano, and I will be presenting correlation and skewness. This heat map visualizes the relationships between various housing features and sale price. The color intensity shows you how strongly the two variables are related. Darker red areas means positive correlation. Meanwhile, the blue-colored areas represent negative weak correlations, implying that those variables have little to no influence or even an opposite relationship. So, on the darker red areas, meaning that one variable increases and the other tends to increase as well. From the chart, we can observe that overall quality, garage cars, and first floor area have strong positive correlations with sale price. This means that home with better overall quality, more garage space, and larger first floor areas tend to sell for higher prices. Overall, this correlation heat map helps identify which housing features most significantly affects property values. So on the second part, this graph illustrates how house prices are distributed in the dataset. As we can see, most houses are concentrated on the lower end of price range, which is shown by the tall peak on the left side of the graph. The red line represents the density curve, and we can observe that it is skewed to the right. This means that while the majority of the houses are moderately priced, there are a few houses which has much higher prices, creating a long tail on the right side of the graph. In other words, expensive houses are less common, but they pull the distribution upward, resulting in a positive skewness. And this kind of distribution is typical in a real estate data, where luxury properties are rarer but significantly more expensive than average homes.
So after data cleaning and preparation, we'll now move on to the methodology part, which we conducted two methods in modeling our machine learning. So number one is the automated feature engineering, and the second one is the manual or traditional machine learning method. So in this part, I will be focusing on the automated feature engineering, which automatically creates, selects, and transforms variables to improve model performance without a need for manual intervention. So this algorithms allows us to detect complex interactions and nonlinear patterns among variables, making it useful for improving prediction accuracy when handling multiple variables. So upon running this method, so 5 models were compared. So specifically the stack ensemble, deep learning, gradient boosting machine or GBM, random forest, and the GLM. So as shown here in table 6, stack ensemble performed the best or achieved the best performance with the lowest root mean squared of 25,202.60 and the highest adjusted R squared of 0.8518. So notably, deep learning, GBM, and random forest also produces strong results, while the GLM produced the weakest.
For the manual feature engineering section, to adjust overfitting, validation RMSE was compared with training RMSE, with differences of 1,000 to 4,000 considered mild, 5,000 to 15,000 moderate, and above 15,000 to be severe signs of overfitting. All RMSE values were scaled back to the original price scale for easier interpretation. The light GBM model showed strong predicted performance but substantial overfitting. The stack ensemble proved the most balanced, achieving an adjusted R-squared of 96.39% and an RMSE of 14,710.25. Reducing predictors via stepwise regression using the BIC criterion and lasso increased the adjusted R-squared to 0.9793, but did not eliminate overfitting. Further tuning, including fewer trees and more flexible parameters, produced a model with RMSE 26,780.53 and an adjusted R-squared of 0.8849, showing no overfitting but lower predictive performance. In conclusion, the best performing model was the stacked ensemble with manual feature engineering, which showed high predictive performance but remained prone to overfitting. Reducing predictors via stepwise regression and lasso lessened overfitting, but it still persisted. A non-overfitting model was eventually produced, though it underperformed relative to other manual feature models. Evaluation was limited by the lack of true test set values, and time constraint prevented more extensive mitigation. Models were prioritized for reasonable generalization over lowest RMSE, consistent with best practices in avoiding overfitting.